Hello, this is David Scher. I'm here to go over the homework for Unit 2 and Unit 3 for Physics 572, Introduction to Health Physics. I have returned all these assignments. Many of you did very well, but I want to make sure I cover this information so that you're prepared as we move forward. So I am going to share my screen and go over these, show you how I would have did the homework. There are multiple ways to do it. I might discuss some alternatives as we go. We will see. So the first question is about gamma rays incident on lead. They want to know questions about the kinds of interactions that can take place, etc. So if we have a 1 MeV gamma ray incident on lead, heavy atomic element, then we know that it's less than 1.02 MeV, so photoelectric effect isn't possible. Pair production is not possible. Photoelectric effect is possible. Compton scattering is possible. For 3 MeV, well, we know photoelectric effect is possible. We know Compton scattering is possible. It's above 1.02 MeV, so pair production is possible. It's above 2.04 MeV, so pair production in the electron field is also possible. It's sometimes called triplet production. So there are many different interactions. So what are the relative probabilities of all these? Well, there are several ways you can get this information. One is to look at the graphs that were in the slides or in reference books. That will help you. I'm going to show you a resource that's available on the web that you can look at. It's another one of these databases from NIST, the National Institute for Standards and Technology. It's called XCOM. It gives you X-ray cross sections. So, I am going to pick an element because it's interacting with lead, which is an element. And I'm going to pick the energies that I'm interested in. And so I can put the atomic number or I can put the symbol for the element in. I am not interested in coherent scattering. Coherent scattering is where a photon changes direction after interacting with an electron but doesn't deposit any energy. That doesn't have a tremendous amount of significance for radiation protection purposes. We're often interested in energy that's imparted or energy that's removed from the incident radiation, so that's not, it's often disregarded in radiation safety. I am interested in the total attenuation. I would like to know about incoherent scattering. Incoherent scattering is another name for Compton scattering. It's when energy is transferred to the electron. Photoelectric effect I'm interested in, and pair production. So what are the energies I'm interested in? I'm interested in 1 MeV, and I'm interested in 3 MeV. Okay? It's going to give me a range of energies, a bunch of different energies, but it'll highlight the ones I'm interested in. So here's a graph showing us the total cross-section. The pink line here shows us the photoelectric effect. This blue dotted line shows us Compton scattering or incoherent scattering. This green line on the right side of the graph is pair production in the electron field. And the one that's green with teal with dashes is for pair production in an electron field or triplet production. So you can see the relative probabilities of each at 1 MeV and 3 MeV. But we have data. So let's go down to the data we're interested in. Let's look at, we're interested in Compton scattering, which will be the third column, photoelectric absorption, and pair production. So columns 3, 4, and 5, notice the units are square centimeters per gram. So these are mass attenuation coefficients. And so at 1 MeV, we are looking at 5 times 10 to the minus 2, 0.05. The Compton scattering, what was that Compton? That's Compton. The photoelectric effect is 0.002, 0.018 MeV, square centimeters per gram, and 0 for pair production. Now at 3 MeV, we've got 0.027 for Compton effect, got 0.0026 for photoelectric effect, and 0.012 for the for pair production. We've also got triple production, but it's 4 orders of magnitude lower, 3 orders of magnitude lower. So a tiny fraction, less than 0.1%. Okay, so that's going to help us with our answer. So let me go to my solution, my little notes I made. For 1A, Compton effect is possible, and photoelectric effect is possible. And I wrote down what the cross sections were, that I just read off of those graphs. So for 1B, I want to know what the relative importance of them are. You don't have to give numerical answers. It was sufficient to say Compton effect is larger than photoelectric effect. I think it's helpful to point out, it may be educational for people who have a lot of experience, that this is not orders of magnitude difference for 1 MeV photons in lead. If we use the photoelectric effect as our reference, Compton effect is less than 3 times as much. It is greater, but it's not 10 times greater. Whereas at 3 MeV, if we use photoelectric as our basis, the Compton effect is 10 times, a little more than 10 times bigger. And pair production is 4.5 times bigger. So it's a substantial difference. At 1 MeV, photoelectric effect and Compton effect are relatively comparable. At 3 MeV, Compton effect and pair production are relatively comparable. In both cases, Compton effect is the larger effect. Okay. Let's go back and see what our next question was, and that was kinetic energy of photoelectrons relative to the binding energy. So if there's a photoelectric effect taking place here, the electron will absorb the total photon energy minus the atomic binding energy. So the important point to notice is the atomic binding energies are small. Now, this is the lowest binding energy. So is that the lowest shell, most tightly bound? Is that the lowest energy, meaning the least tightly bound? Either way you answer it is fine. The important point for you to realize is with the photoelectric effect, when photons are very energetic, MeV photons, they're not comparable to binding energy. The photoelectron has almost all of the photon's energy. So if I have 1 MeV minus 90 keV, that's still almost 1 MeV. It's a rounding error for most calculations. So we can ignore, in many cases, for energetic photons, we can ignore the effect of the binding energy of the electron. The important point is to know the scale of energy that's imparted to the electron relative to the binding energy. That, I think, was the goal of the exercise. Question 2. This is about the Compton effect. So the question here is, first explain it. And I think everyone did a good job. It's an elastic scattering. The photon interacts with an electron. It reduces its energy. Electron picks up its energy. Some people describe some of the kinematics of it. Fine, very good. Next question is to derive a formula for the energy of the scattered electron in terms of the photon's incident energy and the scattering angle of the photon. Okay, so here's what I came up with. If you look in the slide, I don't have the slides out right now, but if you look at the slide, the energy of the electron is the initial gamma energy minus the scattered gamma energy. And so we have a formula in the slides for the scattered photon energy in terms of the incident photon energy that is related through the scattering angle. It's involves 1 over this, the denominator. Well, what we have is E gamma minus all this. So if you do a little bit of algebra, it's relatively straightforward. You can come up with this formula for the electron energy based on practically those two. So that's what I did. Some people worked it out just without reducing it to this form, and that's fine too. This is just a simpler format. Let's see. Next question. To be, what is the shift? And in the statement book, it gives you a reference to page 43 of the statement book. There's a formula for the delta lambda. So in the statement book, there we go. What it had was delta lambda is equal to H over MC times 1 minus cosine theta. Well, you can substitute in for H and M and C and make sure you get the units right. But I don't know those constants in my head. I do remember HC. I used it in the first slide. So I'm going to put a C, speed of light, in the numerator and denominator. That way I know HC. And I know MC squared for the electron. That's 511 keV. That way I've got two constants that I know the value of. HC is 1.24 keV nanometers, and MC squared, as I said, is 511 keV. I know that we're talking about scattering at 60 degrees, so the cosine of 60 degrees is 1/2. So 1 minus 1/2 is also 1/2. So the delta lambda just turns into this very simple algebraic or arithmetic equation, and that's what the value is. I think most people got that pretty well. So that's how I did that. I just made the conversion to constants I knew, and I think that's a relatively good way to do it. But you have to be careful about units. You can't put in mass in terms of energy unless you include the C squared. You have to put it in terms of kilograms, and you got to change units, and etc. Let's see. Let's go back to our question. See, what is the maximum energy of the scattered electron for cesium-137? So to do that problem, I use this formula. Where are we at here? This formula that I derived. And maximum energy transfer occurs when the photon comes in and scatters at 180 degrees. That imparts the most energy to the electron. So theta is 180 degrees, or pi radians. And the cosine of pi radians is -1. 1 minus a -1 is 2. So that's where I get the 2 from. And E gamma over MC squared. For this problem, we're doing it said to use photons from cesium-137. So we need to find out what the energy of the photons from cesium-137 is. So we got to look at a data source, find out where we can find that. I chose one place to go is to look at the HPS radar decay data database. And so I can look at cesium, and I can choose cesium-137. And all it's got is 2 betas, but it says does the decays from barium-137 are not included. So we go back and we look at barium-137M. So this is a photon that comes from the barium nucleus shortly after the decay of the cesium-137, within 2.5 minutes. So it's 662 keV, 661.7. We don't need great precision for this. We'll use 662 keV. So we've got the energy of the photon, we've got the scattering angle, and we've got MC squared, the rest mass of the electron. So 2 times the energy of 2 is because it's the cosine is of pi is -1, and we have 1 minus a minus. Well, it's right here. 1 minus a -1 is 2. 2 times 662 keV divided by rest mass electrons 511 keV. That turns out to be 2.591. All that over 1 plus that in the denominator, 3.9591. And that's all multiplied by the energy of the incident photon, 662 keV. I do this equation and I come up with 447.6 keV. So that's what I got for 2C. Okay, straightforward way to do it. Just having to know where to get the data for decay information for the photons from cesium-137. Okay, now we're going to talk about photons, high-energy photons incident on lead. This is 3 MeV photons, and we're supposed to determine what the HVL and the TVL are. And it says you need to determine the linear coefficient first. So we're going to need to get some data. Let's go find some data. And we will use our mass attenuation coefficients. Isn't that a good place to go? And so we are going to look at the data for elemental data because it's incident on lead. Go back to 100%. There we go. And lead is right here. This is what the graph looks like. So we could just try to interpolate it, but we can also scale down and see what the data is. So for 600, this is for 3 MeV. So here's 3 MeV. The first one is the linear mass attenuation coefficient. This is the energy absorption coefficient. We're shielding. We're talking about the 10th value layer is how much is necessary to remove half or 90% down to a tenth of the original value. For 3 MeV, I've got 4.234 times 10 to the minus 2. So let's go to our homework. Let's see. Oh, I'm going to go to the next slide on this. Next homework. Let's find it. So page B. So the mass is 4.234 times 10 to the minus 2. That's what I just looked up. Now, as the density of lead, where do I get the density of lead? Let's go back to this. So these are the mass attenuation coefficients. One step back. It tells me here that I've got a table that shows me the material properties for elemental media. Elemental media, I'm looking at lead. So let me find lead right here. And this column on the right is our density, 11.35. Density of 11.35 grams per cubic centimeter. Okay? Now, I'm getting many people can get lead from many places. You can go all kinds of sources for physical data. I'm using data from the same source the attenuation coefficients come from. That way it's going to be internally consistent. This is the density they used when they calculated the mass attenuation coefficients. So when I unwind that density, I think it makes sense to get it from the same source. So 11.35, this is the wrong one. So let's go back here, close it and get the one we want. 11.35 is mu over rho times rho. I multiply those two together. And this is the attenuation constant, in linear attenuation constant. That's how much is it absorbs per centimeter. What fraction is absorbed per centimeter? Now, the half value layer, it's reducing the amount of material by half. That's an ln2. So e to the minus mu t is equal to 1/2. And if I unwind that and take the logarithm of both sides, invert it because it's a minus mu t, I get that the half a layer, the thickness, is ln t over the linear attenuation coefficient. I do that calculation based on that constant, and here's what I get out, 1.44 centimeters. Now, the other question it asked me was, asked me what the TVL is. TVL is 10th value layer. How much material will reduce the value of the photons by 1/10, by a factor of 10. In that case, same thing, e to the minus mu TVL is equal to 1/10. E to the mu L, mu times HVL is equal to 10. Take the logarithm of both sides, get the TVL alone. TVL is equal to the log of 10 divided by mu is 4.79 centimeters. Now, the problem's B. It says, based on this information, what's the thickness to reduce it to 6.25%? So some people, and this is perfectly legitimate to do, went back and recalculated all this. Only instead of 2, they put in 0.0625. Well, one of the things that's helpful to realize is 6.25% is a half to the 4th power. It's 4 half-value layers is how we got to 6.25%. And I think the person who wrote this question in the first place wanted people to help recognize that one easy way to use round numbers where it's a 16th, you just multiply 4 half-value layers. That gives you a reduction of 16. And so 4 times the half-value layer is 1.44. 5.76 centimeters of lead will reduce it to a 16th, 6.25%. The other part of this was, based on the information we got in Part A, what would be necessary to reduce it to 0.1%? Well, we cut it in 10th 3 times, so a 10th to the 3rd is 0.1%. So that's 3 10th value layers will get me to 0.1%. 3 times the 10th value layer gives me 14.37 centimeters of lead. Okay, and then what's the next question? It asks me, can I do that again with concrete? And so I've got to go get some information. I've got to get some data now. So one of the things about this database is it has compounds and mixtures as well. So I picked concrete ordinary concrete. And it gives me the attenuation coefficient at 3 MeV right here. It's 3.701 times 10 to the minus 2. So, well, this is, wait a minute. Did I read the question wrong? Let's go back. Oh, I did the problem wrong. I guess we can mark me off. I did the problem for cesium-137. So let's do it. Let's just do it right now for 3 MeV photons. So let's go back and we'll do it now. 3 MeV photons is 3.7 times 10 to the minus 2. So we're going to calculate here. Ln 2 divided by 0.03701, right? And that gives us, ta-da, 18.73. 18.7 centimeters of lead is a half-value layer. And if I make it 10th value layer, ln of 10 divided by the attenuation coefficient, that would be 62 centimeters. So it's a lot more material. It's 60 centimeters is more than a foot, more than a foot. So 30 centimeters a foot is almost 2 feet. It's more than 2 feet. 30.5 centimeters is a foot. So 62 centimeters is more than 2 feet. And the question is, which material would I prefer and why? And the answer is, it depends. Like in engineering, it always depends. Concrete's pretty cheap, and lead is pretty expensive, and lead's hard to manage, hard to control. So I might prefer to use concrete, but sometimes in some applications, I don't have enough space for 2 feet of concrete. And so I might want a thinner shielding made of lead. And there's always an option that I might make a composite shield made of both. And we'll talk more about shielding later in the semester, where we deal with how we construct composite shielding and why. Okay, so that's what I got for homework 2. I believe that's everything. Let me make sure. Yeah, that's everything I got. I gave a wrong answer here because I interpolated to get it for 662 keV because I had that problem on the brain. I was not thinking clearly. Fortunately, none of you would ever do that. So now I'm going to go to homework 3 and start with the problem 1. Let's try to get this one resolved. So describe the mechanisms by which beta particles interact with matter and the main components of the stopping power. So beta particles, electrons interacting with matter. When electrons interact with matter, there are 2 components that I think this is driving at. One is there's a collisional interaction because of Coulomb interactions, where energy is imparted to the atomic electrons through the Coulomb force. The other is electrons can interact with the atomic nucleus and emit bremsstrahlung as a consequence, radiative stopping power. Okay, let me see what my answer was. Oh, and I probably closed it. So let's go with homework 2 or 3C. So that's my other wrong answer. Let's zoom in. And so there's a collisional stopping power, radiative stopping power. Let's see what the other question is. Explain what bremsstrahlung is. Bremsstrahlung is energy that's emitted as photons because electrons are decelerated in an atomic nucleus. Okay. Now, 1B, let's say there's 6.4 milligrams of potassium-40 in the human body. Now, this is similar to a problem we did yesterday. We have a certain, on homework 1, we have a mass of material, and we want to know how much activity is being presented. So, this is a little bit tricky. It's going back to a previous homework problem, or something we learned in assignment in the first side. So the key thing is that the activity, the number of decays per unit time, is equal to the decay constant times the number present. So this is dN dt is equal to lambda. Lambda dN dt is equal to lambda times lambda n, the number that are present to begin with. Okay, so activity is lambda n. So we need to find out what the n is, what the lambda is. So let's get some information. We have 16.4 milligrams of potassium-40. We look up the atomic mass of potassium-40. It's 39.96. It's probably good enough to just stick with 40 grams per mole, but 39.96 grams per mole. So we have 16.4 times 10 to the minus 3 grams. There are Avogadro's number of atoms in a mole, and there's 39.96 grams in a mole. So this tells me in this sample, I have 2.47 times 10 to the 20 atoms. Straightforward. Simple, something you did in freshman chemistry, I assume. Now, let's figure out what the decay constant is, because I need lambda n. That's the half-life is how much it takes to decay half. Lambda is ln2 over the half-life. So if ln2 over the half-life, let's go back and do that, because I've got a calculator here somewhere. ln2 divided by, what did I say the half-life was? I just looked it up. I didn't look it up. So let's find out what the half-life is. Let's look up the half-life. Let's go back to our decay data. Let's go back to potassium. And let's go to potassium-40. We need to get a half-life. The half-life is 1.28 billion years. Okay? A sizable fraction of the age of the Earth. So 1.29 billion years. So go back to our calculator. So ln2 over 1.29 e billion years. And that's our decay constant in per year. Now, I want to convert that now to per second, because that's what we want to find this out. So I've got to, this is per second, so I want to put 1 year is how many seconds. So I'm going to say times 1 year divided by how many seconds are in the year. In a year, 3.156 E7. That's just a number I happen to remember. It's approximately pi times 10 to the 7th seconds in a year. Okay? So I end up with 1.7 times 10 to the minus 17. Let's see if I got my work right. 1.7 times 10 to the minus 17 per second. Okay, so I multiply the decay constant times the number of atoms I have, and I get 4,250 becquerel. I want to make one comment. I see a lot of people giving me answers with as many decimal points as your calculator will present. We're only given the mass of potassium to 3 digits, 16.4 milligrams, not 16.3998, not 16.4010. It's only measured with an accuracy of 3 digits. So in the end, I should only present results that are about the same level of accuracy. This has got 4 digits. I should mark myself off. It should be 4250 becquerel. I'm not marking anybody off for this, but we should not present results that appear to be more precise than we can really validate based on the data we're using. Okay, but I'll carry 1 extra digit for intermediate calculations, and then in the end, I'll try to get to my correct answer. So 1B, the question was, estimate the total activity in the body and estimate the beta energy rate. Okay, so now I got to figure out the beta energy. So let's go back to my decay data. The beta particle is the average energy, mean energy for beta particles from this transaction are 560.6 keV, 0.5606, and it occurs 89.3% of the time. So let's go back to my calculation. And so 89.8927% of the time, that frequently, I get 0.5606 MeV, and there are this many transformations per second. That multiplies out to 2125 MeV per second. Sometimes people forgot to put the abundance or the yield. That's important because not every decay in this activity results in a beta particle. So what is the competing transformation that's possible? The other possibility is not shown here. So let's go look at the chart of the nuclides, and let's look at K40. So K40, look, it's got a black one here and a black one here. K40 is unstable, but it can go either to calcium 40 or it can go to argon 40. If it decays by beta minus decay, let's go to the tab for decay radiation. If it undergoes beta minus decay, right here, it ends up as, where are we at here? Let me make this smaller. And I'm going to show you how to read these. We end up being calcium 40, potassium 40, beta minus, calcium 40. This is one higher proton, one higher atomic number, because a negative charge was carried away and an additional positive charge remained in the nucleus. So what is the alternative? Well, it's also possible that it can have a beta plus that results in argon 40. So it reduces the atomic number by 1. Argon 40 is also stable. So that's a possibility. The abundance of that is very low, 0.1%. So not very much. Most of the time, what happens in this case, well, for about 10.6% of the time, is called K capture. Instead of emitting a positron, a proton absorbs an electron and becomes a neutron. And so it also ends up as argon through the K capture process. So this is electron capture and beta plus. So the majority of the time in this branch, 10% it becomes it's a K capture, and it emits a photon of a 1.46 MeV. Very rarely, about 3 orders of magnitude less, it undergoes positron decay. Okay, so those are the modes that are possible. We're only interested in the beta particle. That was the question, what the question is about. We can ignore that very rare positron. It's not going to contribute much to the energy being deposited. And this 1.46 MeV is from the K capture right here that I was talking to you about, or the electron capture. They call it K capture because it usually comes from the K shell. Okay, so back to my assignment. I'm going to use 0.560 and I'm going to use the 89.3%. And that's what I did, and that's what I ended up with. Now the question is about range. Okay, so we're talking about photons. Oh, I wanted to do the range in two different ways. One is we know that the 5606 MeV is the average energy. So this might be typical of how much energy is absorbed in tissue or in material. But we want the maximum range also, because some of these particles are more energetic than the average, and they can go up to 1.3 MeV. How do we find that out? Let's go back to our wrong one. Let's go back to this. Nope. Let's go back to this one and go to this chart of the nuclides. So we have a beta particle that's got this beta spectrum. We want the endpoint energy here, and that is reported right here, the beta max energy, 1.311 MeV. Okay, 1311 keV. So that's what I used when I did this assignment. Let's look at the max, 1311 keV. And where did I get the range? Well, I went on my merry way to find, where is it? It's in here. I think it's in this one. Yeah. I can go to my E star. That tells me the range, right? So let's go to E star and find the database. There's the E star database. I am talking about, what was the problem again? It was about electrons in tissue. So let's go back to soft tissue. E star, soft tissue. Let's pick soft tissue here. So see, there's a skin. Let's go with tissue soft. Somebody chose adipose, and that's fine. I have plenty of adipose, so I didn't object. I want the total stopping power, but I'm interested in the range. So I'm going to get rid of the stopping power as my focus, and I'm going to put the range there. And I am going to see if I can, I don't think I can do this, but see if I can put an energy in there. Submit it. Nope, you can't do that. That's only when you want the stopping power. So I've got to just go here and I've got to look at this. So let's go down. We want 1.3. Well, 1.25 is pretty close. And we were looking at the total stopping power. Actually, collision stopping power is what I'm most interested in. But for range, anyway, it loses energy. That's the range. So, I don't even do, why don't I just look at the range? CSDA range right there. That's the range in square centimeters per gram. I'm going to use 1.25. That's the closest I have. And there it is. 6.163. Okay. So let's see what I got. Did I write that down correctly? The range for 1311. Why do I have a wrong number here? I've got 0.05. I must have read it wrong. So this is the range. That's 1 MeV. Well, I want 1.25 MeV. Well, there you go. I must have read the wrong number off the table. Well, it's 6.163. This is square centimeter per gram, right? Now, soft tissue is, I went in and looked up what it says the density is, and it's 1. So it's 6.163 square centimeters per gram. Let's get on there. And divided by 1 gram per square centimeter is 6.163 centimeters. So that's a lot. Now, most of the beta particles are not at that range or have that high energy. Most of the beta particles are by the average energy. So let's see what it is for half of an MeV, 0.56 MeV. What is the range? So we go back to our stopping power for 0.5. 0.55, that's good, close to 0.56. And I got 0.2, this is the CSDA range, 0.22, 0.2019, so 0.22. And I've got, for some reason I read it wrong again. I wonder whether, maybe I chose a different material when I did it this way. Maybe I did use adipose. But it's 0.22 square centimeter per gram, 1 gram per square centimeter. It's 0.22 centimeters. So that's 2 millimeters. And the question is most of the energy, what does this have to do with dosimetry? Is most of the energy absorbed locally? How much would escape? Well, for most of the beta particles, which are emitted close to the average energy, most of them would be absorbed. But some of them carry a long distance. So beta particles that are close to the surface of an organ or tissue may be emitted, but a small fraction. Okay, now let's go on and look at radium. This is unit 3. We will go on and look at the next one, which is homework 3, page 4. Okay, let's go look at radium-226. So first we need to find out what's the energy of the photon, of the alpha particle coming from radium-226. So let's go back to our decay data. Let's go to radium right here. We were interested in radium-226. It's 1600-year half-life. It's got 2 alpha particles, and some people calculate it for both, 4.6 MeV, but that's 5%, 5.5% of the time. The 4.78 MeV is about 95% of the time. So I'm going to do the calculation just with the 4.783 MeV photon. Okay? Now let's go back to our assignment. See what we got to do. Describe the mechanisms by which alpha particles interact with matter. So alpha particles interact with electrons and ionize electrons. In addition, alpha particles at low energy interact with the atomic nucleus and impart energy there. That occurs mostly when it's at slow speed at the end of its range. So what's the linear stopping power in air for alpha particles emitted from radium-226? So we need to go back to our stopping power equation, and we're going to go to A star instead of E star. I think I can go to the bottom of the page. Let's just get out of here. Let's go to A star for the alpha stopping power. And we want, what do we want? Stopping power and linear stopping power in air. Okay? So we want the stopping power in air. So we want to go and find air. air dry near sea level. And we want, let's look at all of the components. And we wanted the energy of our photon was 4. Let me look and see. I wrote it down on my. And it was 4.7843. 4.78. Okay. So we'll submit that. We see that only near the low energy, when it's a low energy, does the nuclear component add significantly. And below 10 to the minus 2 MeV, 10 keV. So let's go down to 4. I should have an entry for 4.784 because that's what I put in. And here what my stopping powers are. I'm interested in the total stopping power, I believe, 7.848 times 10 to the 2, so 785. 785 is what I'm interested in. What did I put down? Radium-226. 7.8, yeah, 785, right? MeV square centimeter per gram. Now, I need the linear stopping power. That's what it was asked for. Linear stopping power. This is the mass stopping power. So I need to get the density of air. Find out. Here's the compositional data right here. And the density is 1.205 times 10 to the minus 3 grams per cubic centimeter. So that's going to be helpful. Since it's right there, I will include the density of 1.205 times 10 to the minus 3 and just multiply those two out, and I get about 1 MeV per centimeter, 0.946 MeV per centimeter. So that's the answer to question 1. What is the linear stopping power in air? So we had to convert from mass stopping power to linear stopping power. That was the trick for that problem. Next question. If we use a tin foil with alpha particles, what's the minimum thickness required? So we want the range of the alpha particles in tin. Now, in the lecture, we had some formulas that allowed for to relate the range in different materials. If we know the range in air, that is one way to do it. People did it that way. It's a good way to go. We also had a formula to calculate the range in air for alpha particles. Some people solve this problem by that. I just decided to look it up. I'm also going to just look up the range in tin. So I'm going to choose, instead of air, I'm going to go to tin. It's a straightforward way to do it. There's nothing wrong with doing it this way. And I've got the energy I'm interested in. There it is for tin. Here's the CSDA. That's what I want, is the range. And it's 4.778. There it is. This one, I think, was the CSDA range. And there's our 4.7. That's 47. There we go, 4.78. It's 1.097 E minus 2. 1.097 E minus 2. So let's see what I have here. I have 1.097 times 10 to the minus 2 square centimeter per gram. What is the density of tin? Again, I got different answers for different people, but we're going to look up the properties of tin. And in this database, the density of tin, and they used it to calculate the attenuation coefficient. So I'm going to use it to unwind it. It's 7.31 grams per cubic centimeter. So here's my homework. I said 7.31. The range is equal to the range times rho, gives us the square centimeters per gram. Divide out the rho, I get 0.0015 centimeters. I calculate that out to be 15 microns. That's the thickness of tin required to stop these alpha particles. Boy, you can stop alpha particles with a very thin layer of tin. So what's the third question? what is the linear stopping power of alpha, of the two radium alphas in aluminum? We already know the energies, so let's go back to our alpha. You can also use that same formula to calculate for aluminum based on air, etc. I'm going to pick aluminum as my material, and I can submit it again with the energy still in there, and CSDA, and I'm looking for 4.8, so there it is, 4.78. It's 5.474 E minus 3 square centimeters per gram, and I've got that's over row 620. Oh, I don't want the range. I wanted the attenuation coefficient. Sorry, I read the wrong number. So attenuation coefficient is right here. This is the total attenuation coefficient, and that's 6.23, 623.0. So we'll go back here, and I've got 623.0, and the density of aluminum from my database here is, I need to know the density of aluminum they used. It's 2.700. So I'm going to use that number, and I got 2.0. Multiply those together, and there it is. I get 1682. That's too many digits. MeV per centimeter. Or if I do it in microns, it's 0.17 MeV per micron. 168 keV per micron. Okay, what's question 3? Let's go back to our problem and look at question 3. Explain the Bragg curve and its key characteristics. Bragg curve is a graph showing the energy deposition dEdx, or stopping power, for heavy charged particles as they pass through matter. They have the property of having a peak at the end. Electrons follow a tortuous path. How heavy alpha particles or heavy charged particles don't, and so the peak deposition is more useful in that case. And so there's a peak near the end of the range. The other thing about it is, for heavy charged particles, the peak that's at the end of the range is also at the end of the range of heavy charged particles. The nuclear interactions tend to be comparable or larger than the electron interactions. So a lot of the energy that's contributed at the end of the range, at low energy, kinetic energy of the alpha particle, is from nuclear interactions, not just from electron interactions. So, next question, and I don't have it written down, so we'll just answer it orally. How is the Bragg peak used in medical applications? It's used for charged particle treatment for some forms of cancer. This is a relatively new and becoming popular. It's now approved for payment, and that means it's available lots of places. That's, of course, the key to medical innovation, is when insurance will pay for it, then people will deploy it. They use protons, which are heavy charged particles. They deposit energy at the end of their range. And so they can deposit a lot of energy at the tumor depth and spare the healthy tissues that are outside of the tumor volume. It also deposits energy very precisely at a given depth. And so it can more accurately target tumors, as compared to photons, which have an exponential attenuation in the body and are much more difficult to concentrate. And then search the web for a facility near you that offers proton therapy. And I think everybody was able to do that. Just for fun, I'm going to go back here, and I'm going to open a new one, and I'm going to see proton therapy near me. And I'll bet Chicago is the closest place. Maybe Indianapolis. I'm right now in Champaign, Illinois. So let's go to Oftentimes there's here's a map. Yeah, there's one in Indiana University. There is Christie Clinic. Didn't know Christie Clinic had a proton therapy. That's in Champaign, Illinois, Northwestern. So let's see, Christie Clinic Radiation Oncology. Is the Google search just simply wrong? I don't think that they have proton therapy there, but I could be mistaken. So let's go to their website. Technology specialists. I'm sure they have a linear accelerator. I know the physicist there, unless he's retired recently. Yeah, I don't see, if they had a proton therapy, it would be on the main page. So let's see, maybe it's under news. Yeah, they have infusion center. They have no, I don't think they have a proton therapy there. I think that Google just thought I was looking for radiation oncology, and it picked one close by. There's another one in Champaign, another hospital in Champaign named Crop Clinic, also has radiation oncology, but they probably don't want to pay Google to advertise. But there's a proton center in Indianapolis, Bloomington, Indiana, at Indiana University, and another one at Northwestern that's out in the western suburbs in Warrenville. So there we go. And then, of course, there's Mayo Clinic and lots of them all over the place. So I believe I have answered all of the questions. Let's see if there's anything more. Yeah, no, it's just... So I wish you luck. I do need to get a summary to you so we can get ready for the test. Now that I've gone over the homework, I feel a little bit better so people can have accurate answers to the homework, and that will help them study as well. And you'll be hearing